you still gonna take 17 credits next time?
No, I'm taking 15. Just because of the way the schedule is.
Are you taking chem next term?
No, I wish I was right. Because statics runs the same as both lectures.
So you can take chem next year, or you just?
I'm gonna take it at OIT with a bunch of freshmen. That's the only reason I like this. I should have got a surface, Microsoft Surface.
Oh, yeah.
This is like, you open too many apps and you just like,
Oh, yeah.
Yep.
yeah.
I already have my PE. I took CPR this day. I had to do. Did I give you that?
No, it's gonna be neat. Even more needs to be, I know, my stomach was one of them running too bad.
Your
And-
stomach does?
Yeah,
So does mine.
the kid next to me, Michael, I know he can hear it because I can see him like out of the corner of my eye, just like, whatever. I'm in the same boat as you. I'm like,
I don't eat in the mornings. All I've had so far is a granola bar.
I would tell you at 5. Just so someone can, you know, just,
I don't eat it. Oh, I'm almost there. I can't. My stomach will freak out. I will vomit if I eat it.
It's 16 because I'm Wednesday, so it's recitation for physics and recitation. First hour just like, just zooms through a bunch of material, like very briefly, and then we do like a classic period. And the whole time I'm sitting there like trying to keep that stuff. I'm trying not to freak out. Yeah.
That's actually makes me happy. I'm not as far behind.
Just max, dude.
I'll be done by next June.
I like it.
I don't know why. I took it online though. That might be why.
Oh, no. Well, like less.
I've changed my major so many times. They need an art as well as I'm so confused. It says I'm good on humanities, but it's I'm not.
Except for minus school.
So it has 3 extra electrons. You're looking at the, no, it's the Oh, I have to turn that in, okay.
I'm trying to do that, but it's silent.
Oh, I forgot all my pencils.
Yeah. No. No, you were clear. It was just, accidental.
So start drawing out your structure for phosphate if you haven't already. And so on the back table as well, I have a handout of some polyatomic ions. So we'll kind of go over again this concept in a second. So once you're done, right, drawing out your structures, what are we saying? What is a polyatomic? That's also what we're answering with this question. And then does someone want to try to put it on the board for us, a structure, at least a structure? And if you're in the chat, you could also try to describe or draw a structure out. Go for it. Yeah, and it doesn't have to be right, just a starting point. Yeah, I like this one. So this is a good structure, especially to start with. So I'm just copying it over. All right, so looks good. And so, of course, let's all just make sure we're at the same starting point. So, right, let's see who's at the party. So phosphorus brings 5 electrons. Each oxygen has 6, so times 4 is 24. And then we have this -3 charge, so that means we have to add 3. All right, so now we're at 32 electrons. All right, so that's what's drawn here. And then what do we need to add to this structure? So you have the lone pairs. What was the other thing? Oops. Maybe I'll move it over. So remember our formal charge analysis. So let's look at that. I'll put this over on this page now. All right, so let's look at our structure, right? So we have to think about, okay, well, how did we say we analyzed a structure, right? And so, okay, first step, we have to have the correct number of electrons. Okay, great. Now let's look at, is the octet rule satisfied? And looks like everything's satisfied by the octet rule. Just kind of visually, right, looking at that. Okay, looks good. Phosphorus also has 8 valence electrons. Okay. And then the next step was this formal charge, right, that we had mentioned, calculating. And that also gives us an extra piece of information. And so looking at these, right, we can see that our oxygens are all symmetric. So we can just calculate our formal charge for one oxygen, and it's the same. So what's our formal charge on the oxygen? What do you notice? Oh, and then, so question in the chat. I drew these bonds. I try to show 3D structures. So this is drawn as a fat wedge, showing that it's out of the plane of the board. This is my dashed line to show that it's going behind the plane of the board. And these two are in the plane of the board. So I'm trying to show our tetrahedral geometry there. All right, so back to formal charge. So oxygen, 6 valence electrons minus 1, 2, 3, 4, 5, 6 individual electrons on there, minus 1 bond. So that gives us a -1 for our formal charge. So I'd put a little negative on each oxygen here. And then, well, don't forget that our formal charges also have to equal, right, the overall charge of our polyatomic in this case. So let's check our formal charge for phosphorus.
When calculating formal charge for a molecule that has bonds, like for example, there's 4 oxygens, and you're calculating the charge for oxygen, it's just for one oxygen atom, right?
Yeah, so we just did it for one, and then I quickly did, well, they're all the same, right? Yeah, so otherwise you have to calculate it separately. Like if there was a double bonded one, we would do that separately, which we'll see in just a second. So then phosphorus, back to our calculation, so 5 valence electrons minus, so there's no electrons on there, and then minus 4 bonds. So that gives us a 1 plus formal charge, which we expect, right? Because we're trying to get to -3. And so, okay, let's look at this structure for a second and think about what this is telling us. And so this is one valid, and we'll use our term now, resonance structure for phosphate. And so, okay, let's think about, again, well, what is a polyatomic ion, right? So this polyatomic ion is going to be held together in solution. So, right, it's held together by covalent bonded, so it's a discrete, almost molecule, right, except that it carries a charge. So that's the only difference between a neutral molecule. And so again, in solution, and your book kind of emphasizes it, in this page, right, so it's saying that it's going to be discrete in solution. So magnesium sulfate, right, your polyatomic here being sulfate, is going to all stay together, right, because again, it's covalently bonded. And okay, well again, these resonance structures also just kind of give us an idea about the nature of it. And so let's see if there's another valid structure, so valid resonance structure. And so this is one valid structure, right? It follows the octet rule. We have our formal charges. This looks good. But then we have that other little caveat, which says, well, if we have a negative charge right next to a positive charge, perhaps we can get rid of the charge. And so we're going to try to do that. And so I'm going to show you, again, movement is always with our electrons, right? So we want to look at moving a pair of electrons. It doesn't matter which one, because we're going to draw all the valid structures. And so now we're going to move it over to a double bond. And so we can now use our little resonance arrows. So these double-headed arrows show resonance. And again, this is just moving electrons around. And so notice we're not going to break any of these single bonds here, right? These are here to stay. But with our resonance structures, we're going to be adding double bonds and just kind of moving them around. Because again, we're just trying to describe our molecule and how it behaves a little better. And so it doesn't matter which side you start with. And so now we have something like this. So now I'm just filling in my electrons. And so now we're kind of saying, okay, well, our nature is such that, right, we have a kind of a double bond while we have these 3 single bonds. And so let's also look at our structure here. So formal charges are still on these 3 single bonded oxygens, right? So we got rid of these 2 formal charges. So phosphorus no longer has a positive formal charge. What do you notice, though, about your total electron count on phosphorus? What is it? Is it 8 or? So what is it? 10, right? So now we have an extra bond here. That's okay. So phosphorus can go hypervalent. And so we could recognize that. So phosphorus now has 10 total electrons that it feels, right? So this is in its structure. And, you know, again, it's okay. But this is why we can, again, argue that this is a better structure in some sense. And really what we're trying to say is the true nature of phosphate is really the average of what's going to be all of the 5 structures, right? So now we can continue. So let's draw all the other structures. So moving our double bond around, because again, we're trying to show that it's an average.
The double arrow means that it can go this way or that way.
Yeah, so it's resonance. So resonance is again just showing like electron movement and where like electrons could be occupying essentially. And so again, moving it around. So right now I'm just trying to draw all the possible resonance structures to show you. And let's see, which one am I missing?
Does that also mean, like, in reverse resonance, that the electrons are breaking bonds and creating bonds as they move around?
So potentially, but so not breaking bonds in the sense of like we're not disrupting our molecule, but like later on you'll see that with reactivity, right? It's like something can be reactive because you can kind of move your double bonds around. Or like maybe those electrons that weren't a double bond can attack later, like something like that. But yeah, the key with resonance is that you want to keep your single bonds, and again, you're just moving around your lone pairs or something else to give you that. All right, so then I'm just trying to draw my last one here for completion's sake. And again, put your negative charge on our single bonded oxygens, negative formal charge. All right, so I'm just trying to zoom out. And so again, right, the point of drawing all these resonance structures is, okay, well now we can look at them. And again, we're saying if we could just average all of these resonance structures, right, this will give us the true nature of phosphate and really, you know, again, reflect computational values that we'd be getting. Because again, what we're thinking about is like, where is the electron located? So again, like electron density wise, we can see it from our first structure. So obviously the oxygen is going to be carrying the negative charge, right? That's true in all of these structures. It's just sometimes, right, we have an oxygen without a charge. And then, so notice we also have kind of this double bond that gets averaged out. So we have, you know, 1, 2, 3, 4, 5 bonds for 4 substituents, right? So like, you know, roughly 1.25 bonds or so. Again, just approximately staying. So we might expect that to be reflected too in its bond length, that it's going to be a little bit shorter than just a single bond. But obviously it's not as short as a double bond, right? Because again, it's the average. We just have this one double bond average throughout. And again, you see that electron density just always on the oxygen. So again, telling you where it's located. So does that kind of make sense with these resonance structures and the information that we're trying to gather from it? All right, how do we feel on these structures? So do we feel decently about making kind of polyatomic ions and structures, and or just drawing Lewis dot structures in general?
I have a question about how formal charge of the atoms plays into that. Like, let's, I don't know, this would be too difficult, like hypothetical question, but let's say like the formal charge of phosphorus know what to do with that? You know, if you see that it's not immediately neutral, or would that be something you run into?
Yeah, I mean, so that's where, like, especially if you had like a 2+ charge or something crazy, that's where, again, you see, is there a negative charge next to it? Like, kind of like in this situation, right? Where we were able to cancel it out. You know, that being said, you know, it may not always be canceled out, you know, and then that shows you that your atom is weird, and if you end up with like a 2+ charge on something formally, then you're saying like, yeah, the electron density is not located there, it's somewhere else, and right, there's something else with that negative corresponding charge showing kind of where it is. And then, so for these phosphate ones, it's really all of them. So on an exam, you'd want to include, you know, all of these structures for the best answer. At the very least, like this one, and then show, right, that there's resonance, and then kind of tell me, right, double bond repeats. But, right, that's the whole point of these structures, is that it's not just like one that's kind of the correct structure. It's like looking at it, averaging them out, and again, kind of going back to how it behaves. And with that, right, think back again to the CO that we left off on. Right, we had done the CO at the end of our last week's lecture, right? We had ended up with this weird formal charge where we had that negative formal charge on the carbon as opposed to, right, we would expect it to be on the oxygen, but then that's again where it led to reactivity. So it's kind of everything into play, if that makes sense. So with these resonance structures, you're trying to get kind of all the possibilities to really capture, you know, its true, again, nature and reactivity. Because we're trying to like understand its nature and reactivity from just these little like chicken scratches in a way, you know, versus computational chemistry. And it's like trying to make that, bridge that gap.
And then like, when you look at a polyatomic ion and you're drawing out the Lewis structure for it, how do you know, like what, was there something that told you that phosphorus can be hypervalent and it can have 10?
Yeah, so that's just like knowing how things react. So then at some point you have to be told that, especially on this, starting on the third row, these can go hypervalent.
Okay.
And then the reason is really a size argument. The problem is you'll probably see it in textbooks where they say something like, oh, phosphorus can invoke the d orbitals, which, right, you can already tell that doesn't make any sense because phosphorus doesn't have any d orbitals. And then if you were to look at arsenic compounds, it's still not invoking d orbitals, which I think you've kind of gathered, right, that these d orbitals, if they're filled, they're satisfied and not really participating. So yeah, it comes down to a physical size argument. And so basically nitrogen can't fit. So NF5, now I'm going on a tangent, but basically nitrogen is just too physically small to fit all the fluorines around. It has, that's it, yeah. So that's why they're hypervalent at that level. All right, so let's start looking at chapter 10. We can always revisit these structures if people are feeling iffy about them. And I want to go through chapter 10 because it is just kind of like hodgepodge the chapter in a lot of ways, and like we're also learning kind of like our, you know, classic chemical reactions, and so that's what it's going through. But again, I always feel like your book has a lot of dense information and sometimes in a crazy fashion. And so we start off with chapter 10. We're just looking at these classic synthesis or combination reactions. And so the first thing to note is just kind of the general formula of these things. So basically you have two products coming together to make one product. So right, you're combining them, so you should have fewer products. And so we can look at maybe a most simple combustion where you're literally just adding oxygen to some sort of metal. So either in this case, carbon plus oxygen gives you CO2. Or you could, of course, this is our rusting formula, right? If we take iron plus oxygen, that gives us iron oxide. So formally, that's a combination reaction. Let's look at a video at least. So this is sulfur. So just, elemental sulfur. And it doesn't really burn in the air. They have a flask where they've collected oxygen. And so it does burn pure oxygen here.
This is how to get in shape fast.
The best way to burn fat and get shredded is not keto, it's not paleo, it's not vegan, it's not carnivore, and it's definitely
No,
not.
go away, be quiet. All right, so that was, we'll just write what that reaction was. So again, pretty simple. So sulfur plus oxygen. So probably make some sulfur dioxide. I wanted that light off. That is the one light I wanted off, not everything else. I'm gonna try again. Fitness ads are playing. I don't know. I don't know why we can't turn off the front lights. All right, so again, just two things combining. And so here's another one. So sodium oxide plus CO2 gives us sodium carbonate. And so then your book, again, goes off on this kind of tangent thing, this ions in solution. And again, all this is to emphasize that, right, your polyatomics stay together. So that's one thing that it's emphasizing here. And then so the other thing to think about that your book is trying to get at is, so it's also mentioning how strong these forces are, right? So now we have to kind of think back to our crystal lattice energy chapter. And so we're kind of thinking, right, again, well, there's a lot of stability in here. So this is stable. And so that means, right, that these intermolecular forces are fairly strong. And so then also what we're getting into, so we're putting a lot of ideas together. So, right, water being polar is starting to come out again. So, right, water again has these two lone pairs on this side. So that's going to make it have what we call this partial negative region. So again, meaning that that side of the water molecule is negative, right? A lot of electron density. And so you can see with our little depiction here, so we zoom in, there's our oxygen side, and it is nucleating, right, our positive cation. So I don't know which, I think this one is just sodium chloride that is depicted here. So, right, it's surrounding it. And again, right, you're thinking about solubility in this case, that, okay, these, and we're going to start to use some terms here. But this is, right, our solvent. And then this is what we're dissolving, so solute. So basically, our solvent-solute interactions have to be large enough, right, to overcome these intermolecular forces to successfully dissolve something. And so that's what it was saying there. And then your book makes a big point of, again, emphasizing your polyatomics. And so again, that's why you have your chart of polyatomics, so you know what stays together, what's discrete. All right, I gotta turn on some lights. This is too much contrast. Try. And so then your book wants to specifically talk about what's called oxyanions. And well, all that's to say is obviously a lot of polyatomics have oxygens in them. And so it says, okay, these oxyanions are anything that have oxygen and another element. And so then we can look at kind of the typical naming of these. And so for your exam, I'll let you use your polyatomic sheet just because, again, right, it's a pretty fast-paced course. But you're probably going to start familiarizing yourselves with a lot of common ones. And so if you notice, the ones with more oxygens tend to end in these 8 endings. So nitrate is NO3, and then with a -1 charge. And so just think about this one, right? You've seen this one in lab a lot, so nitrate is pretty common, right? Silver nitrate, potassium nitrate, you've probably worked with a ton of nitrates already, hardly even realize it. And then nitrite is NO2 -1, so 1 less oxygen, and nitrites just tend to be less common by nature. So same thing with sulfate and sulfite. And again, we've worked with sulfate salts, magnesium sulfate, plenty of other sulfates, probably calcium sulfate, but not too many sulfites. Salts, again, just not as common for our purposes. And then we have other versions. So now we have these chlorate salts. So hypo, of course, implies less. So we have hypochlorite, which has only 1 oxygen. Chlorite, which has 2. Chlorate, 3. And then you can have the more in this perchlorate. Yeah, except you wouldn't work with chlorate salts. They tend to be explosive. So. And then same thing with bromate. So of course, bromate, BrO3, -1. Bromite has 2 oxygens. Hypobromite, just 1. Then perbromate, obviously 4. And so to name them, we can just name our polyatomic ion. And so, right, this case would be sodium nitrite. We could practice naming one. So what is this one named? So check your polyatomic. Oh,
I have a question. You're saying that, Why would something like sugar be dissolvable in water? That's pretty big molecule, isn't it?
Yeah,
I
so
understand why salt does, but why would a bigger molecule like sugar?
so sugar doesn't go into water that well, right?
In comparison to, say, salt.
Exactly, right? So you probably noticed that, well, especially, me, I'm from the South, so like you try to make sweet tea, right? And of course, if you start with your tea and then you try to just add sugar to it, usually it just kind of stares at you. Yeah, so then you're saying, okay, well, usually you have to heat it up, right? So if you really want to make sweet tea on a regular basis, then you need like some simple syrup made where you already have some sort of saturated solution. But yeah, that goes into kind of the difference between, so again, right, let's think about it then. So, okay, you have sodium chloride, which again is polar, or is ionic, right? So completely separated charges. So our sodium is going to be attracted over here to our oxygen, right? Our chlorine is going to be over here. But then, so let's just look up what fructose looks like. I just picked a sugar. And so we'll get into this later as we talk about more about solubility. But then you have to look at your structure itself and kind of evaluate, like, is this polar, basically, right? So then you're looking at this sugar molecule, and it does have a bunch of OH groups on there, right? So that's going to mean that it is somewhat polar. So then, yeah, you can, get it into water with enough heating and force or, right, energy that you put in. But, yeah, it's not as soluble as salt, yeah.
The polarity of it versus something like sodium chloride, where the sodium and the chlorine actually
Yeah,
are salt and attracted to different parts.
exactly. And even then, so we'll get into this in just a second, too. But it also depends on these solubility rules, so we might as well. Let's skip to some solubility rules for a second, since we're just kind of doing hodgepodge of reaction, if I can find it now. Oh, here we go. And so, right, the next kind of question, because solubility is a complicated question, and so we're going to take a deeper dive into it. I can't remember I think it's second quarter, where we get into really the mathematics of solubility. But we can at least talk about solubility in the most basic Gen Chem sense. And again, just kind of basically thinking about breaking up those lattice forces. And so let's look at this type of reaction. So this is called a double displacement reaction, or double replacement, depending on what you're looking at. And let's actually watch a video. Okay, let's just try. So we have exactly what we have in class or written. And so let's see it, boom. And so right there's the precipitate being formed. So right, that white gelatinous stuff. And so what's really powerful, though, is this is what's driving the reaction forward. And so that's important to appreciate, right, when we're kind of looking at this. And I can't remember if we've done precipitation reactions in this class. I'm sure we will. Oh, yeah, we did with our copper reaction, right? So we're adding our 4 molar sodium hydroxide.
If you have a utility meter like this on the side of your house, you could get paid to go solar for no money out of pocket.
No, be
it costs
quiet.
nothing to install.
Sorry. Yeah, we could, let's put that reaction up there as well. And so we had copper nitrate, copper 2 nitrate, we could say, right? It was aqueous, so meaning it was in solution, right? Just a nice blue looking liquid that you had. And then you added sodium hydroxide to it, and you made, right, copper hydroxide. And then, of course, sodium nitrate. And so now you can go back to your reaction and kind of reappreciate what happened. And so now let's look at a couple of things. And so again, we can look at the basic mechanism of what kind of happens. And so if you notice, you always start with some AB salt plus a CD salt, and then they swap, right, their cations and anions. So even in your copper hydroxide case, right, you just swap your nitrate for hydroxide. So same thing with this silver one that the video we watched, right? Silver was with nitrate, then it got paired with chloride. And so I'll write that. So our new cation with its new anion, and then plus, right, our other cation anion combination. And so the only trick with this is that it has to be driven basically by precipitation or water formation. And so we'll look at a water formation one, but again, right, we saw that in the video, and so why this reaction works is because this solid is formed, it drops out of solution, and then this continues to drive that reaction forward. So kind of, you know, the thing to think about if you had, let's just say, you know, sodium chloride plus potassium nitrate, right? Nothing would happen. So if you look at your new combination, you would have sodium nitrate, which would still be soluble. You would have potassium chloride, which would still be soluble. So really, what would happen is all those ions would just be in solution, right, staring back at you. So again, that's where that precipitation is key. And okay, well, the next question is, well, how do we know whether things precipitate? And so that's where, hopefully you got the handout. So on one side, again, was your polyatomics, and on the other is some solubility rules. So that will help you.
What makes something soluble in, say, fats or oils versus water? Like, I can't think of an example off the top of my head, but I know that there are things that are soluble in oils, but not in water.
Yeah, so if something is soluble in oil, that's going to be nonpolar. So I always think of like hexane as pretty nonpolar. So, right, a bunch of CH structures. And then that's going to be similar, right, to any sort of fatty acid structure. So looking, I just picked some acid, right? So this is just one of your fatty acids. And so again, right, just a CH hydrocarbon structure, basically. So that would make it nonpolar, and so that means like hexane would dissolve or be miscible with this oil.
So would more of the organics be?
Yeah, so organics tend to be like nonpolar, and so that starts to go into why organic chemistry is done with organic solvents, right, and not in water. So usually you can't really do organic chemistry reactions in water. But that would be a desire if you could just like wave a magic wand. All right, so then you can kind of see how these rules dictate. So look at your halogens, and so notice when they pair with silver, Mercury or lead, they tend to be insoluble, so we see a lot of reactions with silver. Same thing with sulfate. And so when you pair it with strontium, barium, lead, silver, or calcium, it's insoluble or at least somewhat soluble.
So, sorry, if it's insoluble, that's when it's going to form this.
Yeah, the precipitate. And so like I said, right now we're just kind of taking a simplified approach, but later we'll get into quantifying that. And so I did want to bring up just calcium sulfate so we can look at where we're going eventually. Because calcium sulfate is always one of those ones like, is it soluble, is it not? Oh, it's slightly soluble. And well, that's because we really have to get down to the math of it. So we can see, right, this is its solubility, 0.26 grams in 100 milliliters. So yes, right, it has some solubility, but not a lot. And like I said, we're going to later quantify it, right, where we can kind of use these properties to our advantage. Yeah.
So going back to my sugar example from earlier, that would also only be partially soluble, right?
Yeah, or like, right, soluble to a certain extent. So that's where, and then, you know, you could look up the exact solubility. So sugar, and in this case, fructose, let's see if it has, this one has 400 grams in a liter for sugar. But yeah, it all depends on like polarity argument, so that sort of thing, and these intermolecular forces.
It looks like there's a heat element there as well, at 25 degrees Celsius.
Yeah, it's still pretty mild though, right? Because room temperature is about 20, so yeah, like mild heating. But yeah, that's something else that you'll notice with the solubility is sometimes, you know, it mentions like a heating thing, so it's not always straightforward. And so now, again, just kind of looking back at these rules and how to use them. And so if you kind of notice, so all these group 1s and group 2 tend to always be soluble along with ammonia. So ammonium, so ammonium's always soluble. And then hydroxides and sulfides tend not to be. And then again, right, you usually have those confounding ones of calcium, strontium, barium, where they're going to be on that limit, but you know, just kind of assume it's insoluble, especially if it's a double displacement reaction. And then we have our carbonates and phosphates. Again, those tend to be insoluble unless it's with group 1. Then do we name our name over here? Oh, so what was this one's name? We got excited.
That was ammonium phosphate.
So ammonium phosphate, excellent. So right, just name the polyatomics in the naming. So whether it's the cation, but really you only have ammonium as your only cation, and then all your others are anions. See, let's maybe take a break for now. So let's take a 10-minute break and then we'll kind of keep going through these hodgepodge reactions.
Do we skip over chapter 8 and 9 for
Yeah,
we only have up to chapter 7?
yeah, we hit them back in the second quarter.
And then last night, I was like,
All right, let's look at some other reactions. And so you're booked through in here, these group 1 and 2 metal oxides with water. And so again, it's mainly just these group 1 and 2 metal oxides that exhibit this behavior. So let's watch another video for this one. And it's not too exciting, but so let's look. So we have our sodium oxide and water. This is phenolphthalein. So our indicator. Oh, let me see. Right, we just have our sodium oxide. It basically just looks like it's dissolving in there, so nothing's really, again, too fascinating, at least how it looks to our naked eye. But then what they're going to do is put some phenolphthalein in there. I'm just trying to shake it up, just showing you what's happening. So the interesting part, though, is of course now we add the phenolphthalein, and so that strong color, right, is now an indication that it was actually making hydroxide ions. And so again, right, that's what's shown here. Oh, there's my pen. Right, so that reaction is shown here with our, again, group 1 and then group 2. But then your book does point out that like other hydroxide or other oxides don't do this. So for instance, aluminum hydroxide in water would just give you no reaction. So, right, you could add it in there, shake it up, and then put some phenolphthalein, because again, right, it didn't really seem like anything was happening, honestly, right, when we looked at it. Didn't look pretty remarkable, but it was, something was going on in there, and yes, we formed sodium hydroxide or barium hydroxide. So again, that's what the phenolphthalein showed us. And so with that, your book starts to get a little into like acid-base chemistry and kind of what is an acid in solution. And so kind of there's a couple of things to this. And so first of all, there's a couple of ways to kind of show what acids are. And actually, I don't even like this one, so let's back up even further. So let's just talk about a couple of things. So let's go to the auto-ionization of water. And so all that is saying is, well, if you have two water molecules, this starts to go into reactivity. So they're staring at each other. A small percentage of them will ionize. And so what this means is that this oxygen is going to attack. And so then it can deprotonate. So those electrons go over there. And so now we've made our hydronium. And so now we can see, right, oxygen has this weird formal charge on it as well. So that's where our formal charge came from. And then we also have hydroxide. So there's our hydroxide. And this is also to say that, okay, this is our H+ ion or hydronium. And chemists, though, are lazy and sometimes just write H+. But what this is kind of also trying to show is that an H+ ion would never just exist like naked in solution. So it would immediately be taken up by this water molecule and make the true form of hydronium. And so then we can look at kind of organic acids. Again, just kind of a brief peek into the future of where we're going. That's all that your book is trying to show here. And if you can recognize this, so this is acetic acid. Oh, I can't spell. And so you can tell, oh, there's my acetate there. So CH3COO. And so now you can see why some people write it in this form. So acetate. You can also see it written, right, as obviously just C2H3O2. But just kind of get used to it, seeing it in different forms. And then, okay, now we're getting into this concept of the acidic proton. So basically the acidic proton of a molecule is going to be the one that's susceptible to deprotonation. So meaning it could pop off like that, but it really doesn't pop off. It's much more proper to show a little water molecule coming along, and then it's going to pluck off that hydrogen. So then leaving us with our acetate ion again, and lazily shown as H+, but really know that that's hydronium. And so then we get into acids. So we could talk about our simple acids, right, like hydrochloric acid. And then we have, so sulfuric acid is another common one. So sulfuric acid is used in like fertilizer or batteries. And other things to note, so sulfuric is a diprotic acid, since it has 2 protons that it can lose, as opposed to hydrochloric acid, which just has the 1. There's the acetic acid again. So right, it has the acidic proton highlighted here. So again, showing you which one it's losing. So right, oh, that one. So obviously acetic acid is vinegar. Nitric acid is used in fertilizer or explosives. Citric acid, let's actually look at a picture of citric acid. So citric acid is obviously found in lemon juice and limes, but I just want to point out it's acidic protons. And so citric acid is interesting as well. So look at that H3. And so just kind of give you an idea. So it's going to be this hydrogen, and this hydrogen. And so this is actually a carboxylic acid group. So that's starting to get into other organic functional groups, but just trying to get you to see, oh, there's my proton there. So that's, again, kind of where we're going. Carbonic acid. So this is, again, right, just made from CO2 plus water, of course. In beverages, this is, of course, a huge part of the whole carbon cycle. If you want to get into it, right, so your whole ocean acts as an entire sink to dissolve CO2 and release CO2. So giant acid-base chemistry. And then HF, that's used for metal cleaning and glass frosting. So usually they make like microchips with HF. And I'll put this concept and idea on for now. But funnily enough, so hydrofluoric acid is, of course, very dangerous, but it's also a weak acid in the sense that it does not fully disassociate. So we'll come back to this concept. I'm just kind of putting it out there that there's still a lot to kind of get into with these acids. And then phosphoric acid, this is also used in like sodas. And again, right, note the 3 protons there. So again, triprotic acid for phosphoric. You can, again, kind of think about the structure now of phosphoric acid, right? You drew out phosphate earlier. So you can imagine, right, you have your little phosphate all discretely bound together, floating next to, right, your hydrogen ions. So just kind of giving you a sense, right, what's going on. They're floating around. And obviously that's my quick structure here. All right, we looked at that nomenclature. And again, really quick, acid-base basics. We're going to get into this later. So again, we're kind of seeing this with our acids, that they produce our H+ ions. So at least that's a big picture to take away for now. And then you may know this, just eating a lemon, right? They taste pretty sour. Obviously, they neutralize bases, which we're getting into why we're covering it now. We've seen that it turns blue litmus paper red, and then, right, it reacts with metals. So we've seen this like magnesium and hydrochloric acid to give us, right, magnesium chloride and hydrogen. And then, again, bases. So just think about soap. So hopefully y'all haven't had your mouth washed out with soap, but they, right, you know, they at least feel slippery. So if you were to taste them, which I don't recommend trying to taste bases, they would taste bitter. And then again, bases produce hydroxide ions, which right now, right, we're seeing, oh, that's what we use that phenolphthalein for. Right, so that's at least important right now with kind of our basic understanding is like use phenolphthalein to check for hydroxide ions. And again, we'll see they neutralize acids to produce salts in water, which is where we're going with this basically.
I have a quick question. What is it, I don't know if you know this, what is it about acids and bases that make them taste the way they do? Like, how do they interact? Or a biochemical question, I guess. But.
Yeah, I mean, I feel like that's more a taste bud question too, because I assume like those little H+ ions start like whatever, activate your taste bud.
Right.
Yeah.
So it's probably the hydrogen, the excess hydrogen that makes it sour?
I assume so. So we have to like look at taste bud receptors
Right.
and like, yeah, understand what they're like sensing, but I assume that that's part of it. And then of course like smell goes into play as well.
That's true.
So that's super important. And okay, so where were we going with acids and bases, at least for now? So back to our reaction types. So we said, right, we had these double displacement reactions. So we said, okay, well, they were either driven by the precipitation of a solid, or the other way they can be driven is just like a neutralization reaction. And so sometimes you can also see this written as neutralization or double displacement. And so the products of that are water. So it's that formation of water which is also driving this reaction forward. And then of course, right, your salt is in solution. So
Is
that,
this the same sort of reaction that happens when you take, say, was it calcium carbonate for acid reflux?
yeah.
The idea behind it is that it bonds with
Yeah,
the
'cause-
HCl.
Yeah, so exactly. So, right, so now you can kind of think about at least how antacids are supposed to work. So K, right, it's in your stomach, so do a basic double displacement. So just swapping my cation with my new anion. So calcium chloride, right, rewrite your formula, and then you make H2, CO3s, which of course is carbonic acid, which you then have to recognize that it tends to break down to CO2 and water. So yeah, same sort of thing. And so this is like the fancier version, again, just because a carbonic acid tends to disassociate. So then this is sometimes called, right, double displacement plus decomposition. And so that decomp is just to try to show you that, right, the carbonic acid didn't stay and it became CO2 and water.
So that's why it's so dangerous to take something like sodium bicarbonate by itself. I've heard that if you take too much of it, it can cause too much CO2 with
Yeah, I hadn't heard of that, but like, yeah, it makes sense, like, you know, and like, yeah.
That
And,
would also be this reaction, right? It would just be HCl plus NaCO3, and then you just switch.
yeah, so it'd be like essentially the same thing. So yeah, you're still making carbonic acid. Plus, not to get into like the whole body chemistry, but sometimes, you know, people say like if you take too many antacids anyways, that just promotes more production of hydrochloric acid in your stomach. So
I've also heard people say that it messes up the, because you have a really sensitive biome in your stomach.
yeah,
That can mess that up too.
yeah, which gets into, yeah, obviously.
Just the biology and
Yeah, because like the microbiome of your stomach is obviously very important and not covered here by basic chemistry. All right, so then we had double displacement, so let's go through our other reactions. So we mentioned our decomposition. And so decomposition, we can see, right, that's just one thing turning into many products. We could add our carbonic acid. That seems to be one that we see. And so again, right, you can recognize it that you have more products and you add reactants. We'll come back to hydrates. And then, so single replacement reaction, we've seen some of these. So we've looked at more specifically the zinc one. So not with copper nitrate, but copper sulfate, right, if you remember, but same sort of concept. And so you can see with our single replacement reaction, we always have one metal displacing another metal. And so then this gets into other things. So right now, just kind of appreciate our activity series. And so what this is saying is basically it can only replace, a metal can only replace another metal that it's above. And so, right, let's notice, oh, well, copper's down at the bottom over here. So that makes sense why zinc can replace copper, but, right, we can't do the opposite. So if you were to try to do the opposite reaction of copper plus zinc, I'll just put sulfate, but right, doesn't matter, it could be nitrate, we would get no reaction. So it would just stare at us since copper metal is below our zinc there.
so that's because it's less reactant?
Yes, which goes into, this is really related to redox potential, but we're not quite there yet, so that's why we're just kind of appreciating the chart that's given to us, but we'll get into that. And then what we can also kind of appreciate is relative reactivity. So up at the top, not only do these metals replace, but they're also the most reactive, right? So, oh, there's lithium, there's potassium, calcium, sodium, right? All those we know react violently with water. And then we go down. Oh, well, I know magnesium needs some acid usually, right, to get it going. So probably if you just put it in some water, It'll just stare at you for the most part, but we know it gets going in acid. And then now these, right, they're pretty unreactive. They're going to need acid. And then versus the copper, mercury, silver, where you've seen them just kind of stare at you even with the acid. And so again, that's our single replacement. So I'm just going to write kind of like our general form out, where you have one metal that replaces another. And so you usually know it's single replacement since you're making something in its elemental form, right? Whether that be gas or a metal. And so let's get into kind of another concept for a second. And so we want to get into these redox reactions. So these are really important. And so first we have to answer, well, what is a redox reaction? Anybody know? So redox means that we have this exchange of electrons, basically, or oxidation reduction reactions. I'll put exchange of electrons. And so, right, we're starting to see this. And so let's kind of back up for a second, because, well, we have to understand oxidation states. And so first of all, if we look at our periodic table, right, and we have all our little oxidation states, so we have, right, 1 plus, 2 plus, 3 plus. So the first thing to note is these oxidation states are when they're in a compound, right? So then we have to kind of reorient ourselves, and actually we'll skip down to these notes. And so kind of the first thing to understand is that free elements are in an oxidation state of 0. So that means, right, something in their elemental form has an oxidation state of 0. All right, so then if we go back to kind of this general idea of what we're doing, well, if we're trying to convert an element into an ion or vice versa, then there has to be some sort of exchange of electrons. And so let's actually look at our copper reaction again, since it's fresh on our brain still. And so again, right, we had our zinc metal plus copper sulfate, copper 2 sulfate, to give us copper plus zinc sulfate. And so now we can start to break this down and identify what happened. So zinc, again, it was a metal, we could see that. And so I'm just going to put a 0 here to indicate its oxidation state. And then, okay, copper started off as 2 plus. Again, right, we knew that. Well, we knew it was copper 2 sulfate based off of the sulfate. And then, okay, well, let's look at what happened. So then copper became copper 0, and now we can kind of rewrite this a little clearer. So we started copper 2 plus, right? We want to go to copper 0. Well, if we want to get it back to 0, well, it needed to gain 2 electrons from somewhere, right? And you can, like, literally think about this physically, or think about how electroplating works, right? It's like you have to pass a source of current, right, which is supplying your electrons, and then you could take a copper solution, again, pass current through it, and that would start plating out your copper, right? So basically, you just have to have some sort source of electrons. And then again, right, in this case, we're not using fancy electroplating, we're just chemical plating. And okay, we can see that yes, the zinc did supply those electrons. So zinc started, again, as a metal. So it was in a 0 oxidation state. Then it went to zinc 2 plus, and then again, right, releasing those 2 electrons. So we can see that the zinc supplied those 2 electrons that copper needed to plate out. And again, right, you physically saw that. You saw the copper plating out as that zinc absorbed away, right, becoming aqueous in solution as it again supplied those electrons.
I don't know if I'm completely understanding. Why is the zinc so willing to give up its electrons?
Well, it goes back to oxidation potential, which we're just kind of simplifying with the reactivity series, which now I lost. So, right, let's go back to the single replacement. So it's tied to redox potential, right? But we're not going there yet. So we're just kind of saying, okay, is zinc higher than copper? And so, yes, zinc is higher than copper, so we can replace it.
And that just gives up those electrons.
Yeah,
And
yeah.
that's why it forms a bond with the sulfate, is because now it's missing its electrons. It's trying to
Yeah, so it was a metal, right, and it became an ion because it, again, gave up the electrons. So like I said, later we'll take the mathematical approach to this, right? We'll calculate the reduction potential and all that, but we don't want to get lost in the math. We're just kind of appreciating that if it's higher on the chart, then it can replace anything below it. So I guess I'll write that. So metal higher replaces, and I'll put cation below it.
So theoretically, could you replace something like copper with lithium?
Yeah,
Because it's lower?
yeah, so as long as copper is below lithium, then yeah, we would expect it
Which
to
one would
react.
lose electrons and how many would they lose? The copper would, right?
Yeah, so then
Lithium
you'd,
doesn't really have much to lose. It's, I think, number what, 2, 3?
yeah, so that's where it goes into like equivalence, right? So if we were just kind of doing that, so lithium plus copper sulfate, right? So you would probably need 2 equivalents of lithium, right? Since like you recognize, so lithium is going to go to lithium 2, or sorry, you need 2 equivalents of lithium, lithium 1 plus, and so that's where the balancing equations also has to balance with the redox. So kind of the problem with this, which again we'll get into later, is lithium would react first with the water before it would react with the copper sulfate. So you would have to either do it in another medium or, yeah, pick something else. But
And lithium and water, that would make lithium hydroxide?
yeah. Yeah, so that would probably be a competing reaction. All right, so back to our oxidation reduction. And so now we can kind of go through these terms. And okay, so now we're identifying who's who. So then it tells us, so atoms that lose electrons are oxidized, and if you gain electrons, you're being reduced. And so if we look at our example here, so our copper, right, went from copper 2 plus to copper 0. So we say, right, our copper was reduced. And then our zinc, right, lost electrons. So zinc was oxidized.
Is this how oxidizing things, like, what was the example I asked you about last time? Oh, it was sodium hydroxide. Does it work in a, or not hydroxide, excuse me. It's, my brain's not functioning, you know which one I'm talking about. Oh, hydrogen peroxide, sorry. Like, things like that that are known to be oxidizers, do they do this sort of thing?
Yeah, so like hydrogen peroxide would do it. I just don't have an example. But yeah, it would react with like iron to oxidize
Yeah,
it.
so strong with blood.
Yeah, and part of it. All right, so then let's look at our other example here. So kind of another classic reaction well, I don't know about classic since you probably wouldn't normally do it, but at least classic textbook reaction is this kind of fantasy of sodium metal plus chlorine gas to, of course, make table salt explosively. And so again, this is a nice one. They both start off in a zero oxidation state, right? They're in their elemental form. So sodium's a metal, chlorines are diatomic gas. And then we can write their final oxidation states. So of course, sodium became 1+. So now we're seeing, okay, sodium lost the electrons. And that makes sense, right? So now everything's kind of coming into play. Well, metals should be losing the electrons. That's what they tend to do. And then, yes, my nonmetal should gain the electrons. That's what they tend to do. Again, you can see the equivalence. So not only are they balanced because, you know, they need to be balanced to make our sodium chloride because chlorine's a diatomic, but we have, right, our electrons being exchanged. And so we could look at this one. So again, another redox reaction. So this is a combination reaction or synthesis, right? Two things coming together. And so again, carbon is in its elemental form, oxidation state of 0. Same with sulfur, oxidation state of 0. And then notice you want to base the carbon off of the sulfur in this case, especially because carbon can be pretty tricky, which we'll see again later. And sulfur, though, is almost always -2, so -2 times 2, so that gives us +4 for carbon there. And so again, right, carbon loses electrons, it was oxidized, and sulfur gained electrons, so it was reduced. And so again, right, you want to assign your oxidation states. And so it kind of brings up this oxidation states are not charges. And it's like yes and no. So oxidation states, right, they're going to match their ion charges when we're talking about ionic compounds. But then in other things like covalent compounds, then they're kind of considered more bookkeeping. And that's all to say, too, is like an ion charge. Again, you would measure them for an ionic compound, right? You can measure like what their charge is discretely versus, again, oxidation states are kind of more electronic bookkeeping. But again, I'm going to say that this is like more relevant for organics. The statement about oxidation states not being charges. So when we do organic compounds later, we're going to revisit oxidation states, but we're going to see, yeah, that's more bookkeeping in that sense. And so we want to be able to at least assign oxidation states. And so, of course, these are kind of the rules for it. So again, most important rule is, well, if something is in its elemental state and has an oxidation state of 0, and then obviously things like our group 1, groups 2, that's going to be equal to their charge. So that's, again, pretty self-explanatory. And then, of course, the sum of the oxidation states should be 0 or the total charge, if, again, we were doing a polyatomic. And so there's our oxidation states. Obviously, sodium and chlorine add up to 0. And then other kind of helpful guidelines is this is like the order you should do them in. So, right, fluorine is always going to be -1 is what we're saying. Right, hydrogen is usually +1, but don't forget those hydrides. We talked about them kind of briefly in terms of reactivity with metal hydrides. But that's the only time that hydrogen then is going to be -1. So like aluminum hydride, right, iron, trihydride, something like that. So that's the only exception for hydrogen. And then oxygen, so is usually -2. So again, we usually base everything off of oxygen. There's just another exception. And so that would actually be peroxides. So if you look up peroxide, so we can start with just hydrogen peroxide. Well, H2, if we look at this, well, this is 2+. So that means that this O2 is also -2, right? Such that each oxygen is -1. Does everybody see that? And so it's only for peroxide. So peroxides have this kind of general form where obviously R could be as simple as a hydrogen, or we can have organic peroxides with any sort of combination. But again, the point is that each oxygen has a -1 oxidation state for peroxide. And sometimes you see it as either written like this, so O2, -2, meaning that like two of them have that -2 charge. So again, each individual oxygen is -1. So that's the only oddity there with oxygen, is just watch out for peroxides. Otherwise, base it off of oxygen having a -2 oxidation state. And then again, the rest should follow like we expect. Your halogens are -1, your group 6 are -2, and right, nitrogen tends to be -3. And then, of course, okay, we already mentioned that some of our oxidation states for polyatomics has to equal our charge. So we can see that with nitrate. So nitrate, right, is NO3, -1. So base it off of oxygen. So oxygen is -2. So -2 times 3, -6. So that's how we get +5 for nitrogen there. So we'll kind of keep practicing with that. But then the next thing you want to do is kind of go through our other reactions that we've talked about so far and figure out, well, which ones are redox, right? So we can go back, well, synthesis combination, right? That's probably going to be a redox reaction since we're starting with two things in their elemental form, we're making a compound, and so I'll put that, right? So likely redox as well. So just be aware, and then skipping around. So if we go back to our single displacement reactions, oops, just had it. So right, our single replacement, well, those have to be redox, right? That's kind of what's driving them. So those were redox reactions. But then just for comparison, right, our double displacement, these tend to not be. So they are actually not redox. Oh. And you can kind of, again, right, check that. It's like, well, they are just swapping partners. That's true. So they're not really exchanging electrons, and again, right, they're being driven by the precipitation or the neutralization like we saw. So not being driven by electron transfer. So kind of interesting to note that. So again, right, no change in oxidation states, just had a precipitate there. All right, I think we've kind of covered everything. We're pretty close to out of time. Oh, no, we're not. We're actually early. All right, let's finish up hydrates, and that means Thursday we can just do review. Sorry, I was looking at, this computer clock is 10 minutes off. All right, so the last kind of thing to go over formally is our hydrates. And, okay, well, what is a hydrate? So let's look at some hydrates. Oh, geez. Can't spell nickel chloride. All right, trying to show some pictures. And so kind of the key is that we want to say that these things are complex. And so that's what it means by this hydrate, is that if we were to look at the crystal structure, that it would be incorporated. And so you can also kind of see it in their different macroscopic properties. So nickel chloride hexahydrate is this greenish looking powder. And then the anhydrous dry form is nice and yellow. So a little bit different. Let's see if we can, I was hoping they had a crystal structure. Oh, yay. And so this is what I mean by a crystal structure. And so now we can actually see our 6 water molecules in there. So it looks like 4 of them are actually complex to the nickel chloride itself, right? So you can see our nickel, chlorine, chlorine on our z-axis, water bound, and right, kind of note how it's bound. It's those 2 lone pairs of the electrons, right? One pair of them is donating to the metal center there. So kind of interesting, right? Thinking about reactivity, you're always looking at your lone pairs. And then you also have what looks like 2 little waters hanging around as well. Again, incorporated into the structure, which is fine. So that's something that you would do, again, with X-ray crystallography, is you have to like count how many units of water there are per like unit of, right, nickel chloride in this case. And so then to name these, we have to indicate how many waters are complex to. And so we could have the situation of hemi, and that would just mean that we have, right, 1 water molecule for 2 of whatever substrate. So in this case, calcium sulfate can crystallize in that form. And so we have just our little dot here that signifies complexed. So that's what that means, right? So again, right, it's part of its crystal structure. So we can prove this by crystal structure, which is, again, I presume how you prove all of these. And so now we can look at, okay, barium chloride, hexahydrate. And so again, we have all these prefixes, mono, di, tri, tetra, penta, hexa, hepta, octa, etc., right? You can go on, not limited. And so now we have, so barium chloride hexahydrate. So we can see how to name it with our name here, and then write it again with our dot with 6 waters there. Or this other one, so write copper sulfate, then pentahydrate, again showing that it's complex with 5 waters there. Here's just some more fun colors. Again, just so you can kind of appreciate what it looks like, and that, yes, right, their properties do kind of change a little bit as well, either when they're complex to water or different things. So, right, this is showing our nickel 2+, again, hexahydrate in water, so it has that nice greenish color there. And so that's something else that you could do is, you know, get different colors to show how many things are complex to. Right, sure we covered all this. So we did single replacement. So solubility rules. Mm. All right, good. So we basically covered everything, at least in our chapters. So that means Thursday we can probably just do some review. We'll do practice problems, right? Identifying reactions, identifying redox. Anything else we need to practice over? Question? So we'll have a quiz over drawing like structures and stuff. But it might also be stuff like, how many lone pairs are on this structure, that type of thing. So yeah, all chapter 7, like drawing stuff. And then, so I have graded a lot of your stuff. I just didn't put the grades in the grade book this weekend, but I'll be putting that. And then probably come check with me in lab if you're like missing stuff, because I just have like so many papers and it's hard to cart them down logistically. But I have papers so we can find all your missing work. But like I said, give me some time to put them into the grade book, and I'm catching up with your grading, so things will be fixed soon. All right, I guess let's go ahead and end lecture a little early today. And like I said, we'll do practice on Thursday, just kind of putting everything together that we've been talking about. And then I'll hang out on chat just in case there's any other questions, and then I'll see the rest of y'all in lab.
So I have more questions. The peroxides, you said that they have the -2 on the oxygens, is that
Well, -2 for 2 of
2
them.
oxygens instead of -4?
Yeah,
Okay.
yeah, because we would expect it to be -4, but they're -2.
Why does it do that? Like, I think I missed that.
It's just like part of the peroxide structure.
Okay. And is that why they're so darn reactive? Like when I hear what I've always heard about peroxides is they're very reactive with, I know that they use, for example, hydrogen peroxide to bleach things, to clean things because it has a heavy
Yeah.
oxidizer. It's just,
Yeah, I mean, it's
It's
an oxidizer, so that's part of why it's considered reactive, yeah.
okay.
So it probably wants to go back to that 2- state. So
It wants to give out those, it doesn't want those oxygens or?
well, it probably doesn't like being bound together. There's probably something funny about like that peroxide structure that makes it just want to break up and go.
What about things like bleach? Is that also an oxidizer? I think it's sodium
Bleach,
hypochlorite.
yeah, so that would also be like an oxidant.
Interesting. Why are they so toxic?